Hello everyone, my name is Sachin Kathari and I attend Georgia Tech in Atlanta. Today I'll be presenting my second lab report, which is titled Lab 2 Motion of the Falling Object. So let's have a quick review of what we did on our last lab report. Last time we used Newton's second law and we analyzed an object moving at a constant velocity. We found out that the net force is equal to 0, indicating that the final and the initial velocity equal to each other. This time we're actually going to have forces on our object. We're going to have two forces. One is the weight force and one is the drag force. Weight force is the force that pulls the object towards the earth, and this is for an object that is falling in free fall. So the weight force is equal to the mass of the object in free fall times the acceleration of gravity, which is 9.8 meters per second squared, multiplied by j hat, which indicates the direction it's falling in. In equation form, it is more familiarly seen as negative mg times j hat. M being the mass, g is the gravitational force, or acceleration, sorry, and j hat is the direction. Account for the negative for the item falling downwards. The turbulent drag force is the other force that's going to act on our object today, and is the force that pulls the object away from the earth. It is caused by the resistance of air. As the object falls, the air beneath it pushes on it and slows it down. The faster the object is falling, the more the drag force. In this lab, we were instructed to use turbulent drag, in which the object's magnitude is proportional to the square of the object's speed. The general formula for this is negative b times the magnitude of vector v times v cat. The proportionality to the square of the object's speed comes in with 2, with the velocity being multiplied to itself. Let's examine my video and tracker and see how I obtain my data. So for this lab, I used a coffee filter. The mass of it was 0.00099 kilograms. The surroundings were everything in my apartment. The tracker gave us the initial position and also the last observed time. I'll show you how my tracker video looked. Basically, it fell down in a straight line, and that was my center of mass or my point mass. Let's go and go to my code. And so we had two codes, one with drag and one without drag. So I plugged in my ball's mass here as 0.00099. The initial position was also taken from tracker. We knew that the initial velocity was 0, 0, 0 because the item was at rest in my hands, so it was not really moving at all. We set g equal to 9.8 from 9.8 meters per second squared from the weight force formula. J hat is 0, 1, 0, even though 1 is positive here in the y direction. I'm going to count for it later, and the object actually does fall down, so don't worry. B is equal to 0.004985, and that's the proportionality constant. It's called the drag coefficient, and it is actually associated with the area of the object, which in my case was this coffee filter. Is that the surface area of the object, actually? Let's go to my calculation loop. So the t is equal to 1.368. That was my last observed time. We want to be less than that. This is my weight force formula. This is my drag force formula. And this is my total net force. The drag force formula, I'll show you how I derived it to make a little bit more sense. So F, the drag force is equal to negative b. The b is the drag coefficient here. The normal here, normal ball velocity is actually right here. And then the magnitude is right there. As we can see, the negative 1 accounts for the negative sign there. So that should make it clear how I actually manipulated this formula to fit into Python. So I'll play this. Right here is Newton's second law, and this is the position update. Before I play it, sorry, I'm going to show you my arrow scale. I did it the same way it was shown how to do in the lecture videos, 2 divided by the mass times gravity, and I found it. I'll run this and show you how it looks. So if we notice the b value equals our last y position from tracker down here, and that's what we wanted, negative 2.28. And my object fell downwards. This is how we wanted it. This represents the weight force, this represents the drag force, and they cancel each other out. So now, for the object with no drag, it's basically the exact same code, except I hashtagged the proportionality constant b, and I took out everything related to the drag force here. And the only force acting upon this object is the weight force. And basically, this just falls down and down and down in a straight line, and nothing acts upon it. So now I'm gonna compare this on a spreadsheet. Part A and Part C were my experimental and my model positions with drag, and they kind of overlap each other, which is really good, meaning that my experiment was successful. They had a slower velocity than the object with no drag. This is the object with no drag, and it just falls much faster, and it has a steady fast velocity. And then here, actually, we reach a terminal velocity, and this answers one of the questions that we were supposed to, the what if questions, and what does it mean. My object does reach a terminal velocity, and terminal velocity occurs when the weight force is equal to the drag force, so the slope becomes linear on a position versus time graph, which it does right here. And so basically the item is moving at a constant velocity. Terminal velocity, constant velocity, they're the same thing. Now for the second question, if my object was thrown downwards, how would that affect the case, and would the terminal velocity be the same or different? And the terminal velocity would actually be different. It would probably be reached earlier because of the initial velocity that the object is being thrown at. That's going to make more air resistance occur, and the terminal velocity will probably be reached earlier. Not to mention that the object is probably going to not fall in a straight line anymore, or it still could, but in my case it probably wouldn't. But yes, the terminal velocity would be reached much earlier. Overall, the experiment was pretty successful. Thanks for watching, and if you have any questions, please leave them in the comments below.